Another video on my normal distribution sequence. The idea here is right when you start to get comfortable with the normal CDF and inverse norm functions, right when you get the hang of those, understand what their inputs are when you use one versus the other, you see them in a different context. There's the context you've seen them in, which isn't typically even named at the point, but it's called the parent distribution. More on that later. But once you get comfortable with using these things in the parent distribution, which is what we've done so far, you're given two different places to use these. In these next two videos, we'll talk about those two different places. The first is what's called the sampling distribution. And the difference between the parent distribution and the sampling distribution is what the area underneath the curve represents. Whoops. So when we talked about the parent distribution, you could think about the area underneath the curve as representing the probability that one of your observations is in a given range. So let's see an example that we've done. Offensive linemen. If I asked you what's the probability that one offensive lineman weighs between 290 and 350 pounds, that's talking about the parent distribution. But what if I change the problem? What if instead of asking you about one offensive lineman, I asked you about a sample average? I said I went out and I randomly selected 50 offensive linemen, and their average weight is what I'm interested in. What if I said, what's the probability that the average weight of those 50 people, not one, but 50, for example, is between 290 and 330 pounds or something? You'd have to change stuff. What you'd change is you'd recognize that since the question is about the sample average, we need to deal with the sampling distribution. And the good news is the sampling distribution is pretty damn similar to the parent distribution that you've been studying. The main thing that changes is the spread. We're still going to use the normal CDF and the inverse norm functions out of our calculator. And when you use either of those two functions, you still need to know the center and the spread. And what you're going to type in for the center will be the exact same. It'll be the mean given to you in the problem. What's going to change is you're no longer going to use sigma. Sigma is still going to be given to you in every single problem. Has to be. Mu and sigma will be given to you. But you're not going to use sigma as the spread in your calculator. You're instead going to use sigma divided by the square root of n, where n is the size of your sample. So if I had 50 offensive linemen, n would be 50. If I randomly selected 200 offensive linemen and calculated that sample average, n would be 200. Let me give you an example. Suppose the lifespan of a salamander is left skewed. Oh, that's different. I'm used to the shape always being approximately normal. Don't worry about that. It's still going to be approximately normal. I understand that it says left skewed here. Really, what you'll see is this is describing the parent distribution. And even when the parent distribution is not approximately normal, the sampling distribution still can be approximately normal. And it'll turn out it has to be approximately normal in order for you to do the problem. Because in every single one of these problems, you're going to either be using normal CDF and inverse norm. And the norm part of inverse norm, the normal part of normal CDF, is saying the shape is approximately normal. The shape has to be approximately normal. It's going to be approximately normal in your problem, even if your teacher tries to trick you and tells you that the parent distribution is not approximately normal. We're not drawing the parent distribution. We're drawing the sampling distribution. And the sampling distribution will end up being approximately normal. You might be asked to justify why the shape is approximately normal. If you're a wise ass, you could be like, because you want me to use normal CDF and inverse norm, and it has to be normal to do that. But your teacher won't be happy with that answer. Your teacher will want you to say one of these two things. Either because it told me in the problem that the parent distribution shape was approximately normal. That didn't happen here. The parent distribution shape is left skewed here. So it's not this first thing. It's because n is greater than or equal to 30. Why 30? Is there some magical number? What does the sample size have to do with the shape? These are all great theoretical questions that I'd get at if this weren't a video intended for people who are just trying to pass their stats class. Right? Maybe I'll make a separate optional video about the theory behind this. But since that's not my goal in this video, this goal in this video is just to give you the information you need. Maybe you'll just believe me that the shape is going to be approximately normal. It has to be. And if your teacher asks you why, it'll be for one of these two reasons. One of these two things is going to happen in every single sampling distribution problem. It has to happen because otherwise you couldn't use normal CDF and inverse norm. And if you can't use those, you can't do the damn problem to begin with. Anyways, let's do the damn problem. Suppose that the lifespan of a salamander is left skewed with a mean of 20 years. This is still mu. In every single problem, they're going to tell you mu and sigma. Every single problem. That's what they've been giving you, mu and sigma. In the past, mu and sigma were your center and your spread. That's no longer the case. Supposed lifespan of salamanders left skewed with a mean of 20 and standard deviation of 6 years. I had pulled that information out of the problem. Note that I'm not saying how likely is it that one salamander lives between 19 and 21 years. I'm asking you, how likely is it that if I grabbed 64 salamanders at random, the average lifespan of those 64 salamanders is between 19 and 21 years? This is my sample size, the number of observations that I have. In this case, it's 64. And it's the third number that has to be given to you in these problems. In every single sampling distribution problem, it will give you n, sigma, and mu. And they're all pretty different, so it's pretty unlikely that you'd confuse any of them. Always pull out those three values. And draw your picture. I'm going to draw something that's approximately normal, even if it doesn't say approximately normal here, because one of these two criteria will be checked off in the problem, because it has to be. In this case, n is 64, which is greater than or equal to 30, which is this magical criteria that your textbook tells you is needed for normality. Center is still 20. Okay, technically, the center is not mu anymore. It's mu with a little x bar down in the subscript. This is how you tell your reader that you're talking about the sampling distribution. Don't worry too much about that. If you forget that, a lot of teachers won't even care to begin with. All you need to know about mu sub x bar is it's the symbol for the center in the sampling distribution problems, in the problems that talk about not one salamander, but 64 salamanders. And the nice thing about mu sub x bar is it's the exact same as mu. And mu is always given to you in the problem. Mu is 20. And you're like, that's dumb. Why'd you write all that? I'm just trying to make the point that it has a new symbol. There's a new symbol for center. It's not mu anymore. It's mu sub x bar. And yes, those are the same number, but they're different concepts. Maybe it'll make more sense when I talk about the spread. The spread is sigma with the little x bar down in the subscript. Oh, that's nice. Center and spread used to be mu and sigma. Now they're mu with a little x bar in the subscript and sigma with a little x bar in the subscript. X bar is the sample average, which is what the question is about in the first place. Right? The average lifespan of this sample of 64 salamanders. Anyways, sigma sub x bar does not equal sigma. It's the key to these problems. It's equal to sigma divided by the square root of n. That's what I was getting at earlier when I talked about the mean stays the same, but the spread changes. When your calculator asks you for spread, which it will when you use normalCDF and inverse norm, you got to know that if it's a sampling distribution question, don't put in sigma. It'll give you the wrong answer. Put in sigma divided by the square root of n. So in this case, n is 64, and sigma is 6. So I would do 6 divided by the square root of 64. And you pull out a calculator for that or something if you want. It'll turn out that's 0.75 or 3/4 or whatever. Pull out a calculator, trust me. I got a calculator right here. But I'm just going to ask you to trust me. One more thing before I go drawing my picture is often you'll see questions, like if this is on your midterm or something, you'll be asked to justify the shape. The shape is always going to be approximately normal, or you can just write normal. Always, when you're doing these problems. Because otherwise you couldn't use inverse norm or normalCDF. So your teacher's going to write the problem in such a way that the shape of this sampling distribution, which is what I'm drawing down here, is approximately normal. But you might be asked to justify why. If you're in my class, you're definitely going to be asked to justify why. So your answer for why it's approximately normal is either this or this. Either the parent shape is normal. It's not. The parent shape is what's given to you up here. This is the parent shape. And in this case, it's not normal. It's left skewed. But that's okay as long as n is greater than or equal to 30. So I'm going to say it's approximately normal because n is greater than or equal to 30, which it is because n is 64. A lot on the theory, but this isn't just theoretical stuff for theoretical purposes. Teachers will ask you these questions. They'll say calculate sigma sub x bar. Often these three things are asked before you even draw your picture and figure out your answer. If you have a teacher that just asks you for the answer, I suppose you can skip all this and you can just say, all right, I want to know the area between 19 and 21. I'll throw 19 over here and I'll throw 21 over here. Note that I'm not counting up and down by this spread. But if I were to count up and down by this spread, which we did when we first learned these things, I would not count up and down by sixes. In this picture, the amount that you'd count up and down by would be 0.75. This is the relevant spread in this picture. So 20.75, 21.5, 22.25 if I were to count up and down by 0.75. But typically by the time you get to this point in the class, you don't even do that. You draw this picture, say, I want to know this area, because this area is how likely it is that the average will be between 19 and 21 years. Anytime you're trying to find the area underneath the curve, using normal CDF. Anytime using normal CDF, you have to give your calculator 4 inputs: the lower bound, the upper bound, the center, and careful here, the spread, which is not 6, it's 0.75. All right, this is not mu, this is mu sub x bar. Maybe I'll write that in a different color. This is mu sub x bar. It just so turns out that mu sub x bar is always the same as mu. So if you forgot that and accidentally put mu here, nobody would be the wiser because they're always equal. But if you forgot that this was sigma sub x bar, you'd be screwed, because sigma sub x bar is not the same as sigma. You got to take sigma and divide it by the square root of n. That's where this 0.75 comes from. Anyways, throw that into your calculator and you're done. Go to distribution, second and then variables, which is where the normal CDF function lives. We've seen this in previous videos. The lower bound is 19. The upper bound is 21. The center, mu sub x bar, even though I know it says mu right here, think about this as center, not as mu, it's 20. And the spread, I know it's asking you for sigma, but really it wants the spread. If I could remake these calculators, I would change this to say center and change this to say spread. Doesn't want sigma, it wants sigma sub x bar, which is 0.75. By the way, if you couldn't tell that it was 0.75, if you didn't want to do this math in your head, it's totally fine if you put in 6 divided by the square root of 64. And let your calculator figure out what that's equal to. And you don't even have to close the parentheses. Calculator will do that for you. So if you don't want to type in 0.75, totally fine to type in an expression like I did there. And then go down to paste. All right, I'm using the normal CDF function on my calculator. My lower bound is 19, my upper bound is 21, my center is 20, and my spread is this expression. If I hit enter, it calculates the area for me. It tells me this area right here is, I guess in red, although it doesn't really matter, is what, 81.76%. That's the answer to the question. If you have a teacher that just wants to know this percentage, then you don't have to write this stuff over here. But typically what will happen is your teacher will ask you, how come you're drawing something that's approximately normal if it says left skewed right here? And you'll be like, because I'm drawing the sampling distribution, and this is the parent distribution shape up here, and you're just trying to trick me, telling me about the parent distribution shape. But I don't even need that. I need the sampling distribution shape. And the sampling distribution shape will end up being normal, or you can't do the problem. But since you'll probably be asked why, know that the reason why is either because the parent distribution shape is normal or because n is greater than or equal to 30. Let's do some more examples, maybe a little bit quicker because I kind of beat that one to death. We're talking about golfers and how far they hit their 7-iron. Okay, fine. It's approximately normally distributed. Oh, that's nice. They're telling me the shape of the parent distribution is normal. So now I don't even care what the sample size is. I don't even need the sample size to be bigger than 30 now. I don't even need this criteria because the parent shape is normal. So that tells me that the sampling shape is normal, which is what allows me to use normal CDF or inverse norm in the first place. It gives me the mean. What symbol you got here? This is mu. That's 160. They always give you mu and sigma in the problem, even though that's not what you want. You want to know, and I'll write it off to the side here, shape, center, and spread. And you can skip this part if you want to skip this part, but I think what you'll see is you'll be tested on this. Shape's approximately normal? Always. But why is it approximately normal? Well, for one of two reasons. Either because n is greater than or equal to 30. It's not in this case. N is only 9. But that's okay, because the parent shape is approximately normal. It says so right here. This is my parent shape. So approximately normal because parent distribution is approximately normal. How about I just write parent is, and you know what I mean. The center, that's mu sub x bar, not mu. However, those just end up being equal to the same number, 160, always. Spread, it's not sigma, it's sigma sub x bar. That is equal to 12 divided by the square root of 9. Square root of 9 is 3. 12 divided by 3 is 4. If you want to calculate this to be equal to 4, you can. If you want to leave it like this, that's fine too. All that's saying is that if you were to count up and down You would not count up and down by 12s. You'd count up and down by 4s. But we're at the point in the class, we're sophisticated enough, we don't even really count up and down by the spread anymore. You write this off to the side, and that's enough for the reader to understand what you would be counting up and down by if you were to do it, so don't even bother doing it. What is the probability that? There's that key phrase. That's saying find the area underneath the curve. It's not saying what's the probability that one golfer can hit their 7-iron more than 165 yards. If it was, it'd be a question about the parent distribution. It's saying what's the probability that if you grab 9 golfers at random and found the average distance of these 9 golfers' 7-irons, that average would be more than 165 yards. So 165 somewhere over here. I want more than 165, so I'm going to shade to the right. What is the probability that? That's my key phrase. It's a big hint, red flag, if you will, telling you that you want to use the normalCDF function on your calculator. normalCDF always takes 4 inputs. Lower bound, 165. Upper bound, none provided, so I kind of trick my calculator by putting in any arbitrarily large number. Bunch of 9s, E99, whatever you want to do, I don't care. Then put mu sub x bar, which is 160. And then sigma sub x bar, which is 4. Type that into your calculator. I'll spit out an answer for you. That answer will answer the question. We'll move on. normalCDF, lower bound 165. Upper bound, any arbitrarily large number will do. Doesn't matter if it's the exact same as that. Just put in a big number. 160 and then 4. Hit enter, twice actually. And it tells me about 10%. 10.56% if you want to format it as a percentage and round to 2 decimal places. Cool. What is the probability that a randomly chosen golfer can hit their 7-iron more than 165 yards? Wait, what? This looks just like number 1. Think for a minute. What's the difference between 1 and 2? The difference is, this is a trick question. This doesn't belong on this video. This belongs on the previous videos I did on the parent distribution, because it's not asking about the average of 9 golfers. It's just asking about 1 golfer. This is parent distribution. It's a trick question. Why'd I put it here? Because this happens all the time. Once you're introduced to the sampling distribution, teachers go back and they throw a parent distribution question right next to it, because students are so focused on trying to figure out what n is so they can figure out the correct spread that they don't recognize that, well, you don't even need n. When we're dealing with the parent distribution, all you needed was mu and sigma. Mu in this problem is equal to 160. Sigma in this problem is equal to 12. So the setup's going to look pretty damn similar. There's horribly drawn normal distribution. There's my 165. Still want the area to the right because I still want them to hit it more than 165 yards. Still going to use normalCDF. Aren't you going to get the same answer? No, because I'm going to change my inputs. Think about if you know what input I'm going to change. Lower bound still 165. Upper bound is still some arbitrarily large number. Center is no longer mu sub x bar. It's now mu. However, those two things are always the same. Spread is no longer sigma sub x bar. It's sigma. There's the change. My spread is 12. And by changing that last input, it's going to change my answer. If I go back to distribution in the normalCDF function and change this 4 into a 12, it's going to give me a different answer. My answer is now 33.85%. Not to get too far into the theory here, but note that it's a lot more likely that 1 golfer can hit their 7-iron really far than it is that the average of 9 golfers would hit their 7-iron really far. Because think about it, in these 9 golfers, yeah, I might have 1 or 2 that can hit their 7 really far, but then I probably have a few that don't hit their 7 very far. And so I'd expect the average to be closer to this population average of 160. That's why this percentage is less than this percentage. If that made any sense, fantastic. If it didn't, don't worry about it. You're not worried about the theory. You're just trying to pass the class. Problem 3. What is the 75th percentile? Oh, that's another one of those red flags, right? Not every inverse norm question will say percentile, but it's a pretty safe bet that every or damn near every time you see percentile in these type of questions, you're talking about inverse norm. What is the 75th percentile? That's defined to be the point that is so big that 75% of the observations lie below that point. In other words, this area right here is 75%. For the average 7-iron length among a sample of 9 golfers. So this is not for one golfer, but it's the average of 9 golfers. Because it's the average of 9 golfers, we're back to talking about the sampling distribution. So this is where we're about shape, center, spread. Shape is I'm not even going to bother writing it again. Shape, center, spread is right here. And it is very likely that you'll be asked questions about the shape, the center, and the spread when you're dealing with the sampling distribution. And the next topic, by the way. How do I answer this question? Inverse norm. Inverse norm always wants 3 arguments. It always wants the area to the left of the point in question, which is this 75%, which I always format as a decimal. And then the center and then the spread, which are not mu and sigma, because this ain't a parent distribution question, because it's not about 1 golfer, it's about 9 golfers. This is a sampling distribution question. So the center and the spread are mu sub x bar and sigma sub x bar, which are 160 and 4 respectively. Type that all into a calculator. The inverse norm function is also under the distribution menu. The area to the left is what it's looking for there, 0.75. The center, it's misleading that it says mu here. It should say center because it's mu sub x bar. And it's misleading that it says sigma here because it doesn't want sigma. It wants sigma sub x bar, which is 4. As you can imagine, a lot of students end up getting it wrong for that reason. 162.70 if I'm rounding to 2 decimal places, which is what I've been doing kind of arbitrarily. The answer here. That's all I got on sampling distribution. What's the minimum you need to know? Okay, sampling distribution questions are going to look very similar because you are always only going to use the same 2 calculator functions, the normal CDF function and the inverse norm function. So there's still that same challenge about reading a word problem, some context you've never seen before, and telling whether it's normal CDF or inverse norm. But I made a video just on that topic, so hopefully you're pretty good at that at this point. The center is still the mean, although technically it has a different symbol now. It's mu sub x bar. But be careful, the spread is not sigma. The spread's different than it used to be. It's sigma divided by the square root of n. And if you want to get technical, it's got a new name. I don't know if it's super important that you understand these new symbols, but it might help keep it straight in your head that in every problem they're going to give you mu and sigma, and you need to think about mu sub x bar and sigma sub x bar if we're talking about a question that asks about x bar, a sample average. Shape is going to end up being normal because otherwise you couldn't do the problem in the first place. So your teacher is going to contrive this problem to make sure that the shape is normal. Has to be. But you'll likely be asked to justify why it's normal. And there's 2 different reasons for why it'll be normal. One or the other will always happen. The area under the curve still means kind of the same 2 things we were talking about, except instead of thinking about it as the probability that one observation falls in a given range, now it's the probability that the sample average falls in a given range. Not that how likely is it that 1 golfer can hit their 7-iron this far. It's how likely is it that if you got a golf team of 9 people, 9 randomly chosen golfers, that the average would be in some given range. You can also think about it with this second interpretation, the proportion of all. It used to say all observations that are in this range. Now it's the portion of all sample averages that are in this range, which is kind of this hypothetical construct, which is a little hard to wrap your head around. My advice to you is think about it as this first one. More often than not, word problems will be written to have this interpretation in the first place. So yes, B is still true, but you probably don't have to worry about it a whole lot. It's also worth pointing out that when you're writing sampling distribution questions, as I do, I'm a teacher, I write these questions, I make them on midterms and finals and stuff. Inverse norm questions, they're hard to write. The easiest way to get around making them hard to write is by using percentiles. If you don't use percentiles, they're pretty hard to write. So if you see a problem that looks really clunky and it was really hard for a teacher to write, there's a decent chance it's inverse norm. If you see a problem that's really easy to write, like what is the probability that, or what proportion of golfers blank, then it's going to be a normal CDF question. So keep that in mind. If it's asking you for the distance, not the area, then it's going to be inverse norm. I think that's all that I have on the sampling distribution.